All right, after we've looked at our different subatomic particles, I think that it's valuable to think about the periodic table and think about, well, the mass number as well as the average atomic mass. To do one of these calculations, one of the ways that you could look at this or approach this is to say, we have to figure out the average atomic weight of the element rhenium. Now, there are two isotopes of rhenium, 185 and 187. The way that these are denoted, this 185 and 187, both of those are the numbers of protons plus neutrons. The difference between 185 and 187, well, is the difference in the number of neutrons between those two different isotopes. Now, rhenium 185 has a specific isotopic mass of 184.953. The abundance of this is it amounts for 37.40%. Rhenium has an isotopic mass, or 187 has an isotopic mass of 186.956 and has a percent abundance of 62.60%. Now, if you added 37.4 and 62.6, that would add up to 100, which makes sense because this accounts for all 100% of rhenium isotopes. Now, from this question, what we're trying to figure out is what is the atomic weight of rhenium. Another way to think about that is what is your average rhenium atom? What's the mass of it? Well, what you've got to do for this is you have to take the mass of each isotope and the abundance of each isotope. So I'm going to say 184.953. That's the mass of one of our isotopes. And that accounts for 37.4% or 0.3740 of the known isotopes. So I'm going to take those two numbers and I set those up to multiply by against one another. To that, I'm going to add 186.956 times 0.6260. Whenever I take those numbers, now I'm going to use my calculator on my computer here, 184.953 times 0.3740 is 69.172422. Add to that 186.956 times 0.6260. And that is 117.034456. So I've got these two different numbers and I'm going to combine them. So 117.034456 plus 69.172422. And I get 186.206878. Now, a good question here is, well, what's the correct number of significant figures to use? And since we are doing multiplication to start things off, we need to take into consideration the number of significant figures in each one of these numbers. So 184.953 has a total of 6, I'm going to label it SF, or 6 sig figs, and then 37.40 has 4 sig figs. So our answer for each one of these has to have 4 significant figures. Now, for so each one of these will have 4 sig figs. And if you look at the resulting number with 4 sig figs, that's going to be this right here, 69.17. And then 4 sig figs here is 117.0. And so we combine those and we get this 186.206878. Since we did addition, we have to take into consideration how many numbers are past the decimal place. And there's only one. So our answer for this, our best answer for this is 186.2. And units for that are going to be AMU. Okay, well, that's an example calculation. They're pretty straightforward. You just have to think about, well, what's the point? The point is to take into consideration the relative abundances of these. And one thing that I think is a good mental math check for yourself is we can see between the two of these, one has a mass of approximately 187, one has a mass of approximately 185. Our resulting number, 186.2, is closer to 187, is closer to our higher value, which makes sense because that accounted for 62% of our total number of isotopes. All right, I hope that was helpful, and I'll see you in the next one.